time to start. So good morning, everyone, and a warm welcome to EFCA's Machine Learning Coffee Seminar. So I hope your fall semester has started well, and I'm really happy to see so many of you also now here joining the seminar. So before we will go to today's very interesting presentation, a few words about now the organization of the Machine Learning Coffee Seminar. So we are a bit lacking the presentation. So for example, for the next week, we don't have yet a presenter, and that's definitely a lot due to the starting of the academic year and the Academy of Finland proposal rounds. But if you have any good topics or suggestions for the presentation, so please contact me or Markus, and we are happy to book your time to present your work also. And then we will soon start with the presentation, and as before also, so you are available to ask the questions already during the presentation by writing the questions into the chat or raising your hand, so I can then read the questions aloud or give the floor to you. And of course, after the presentation, we will then have good time for a longer discussion. But okay, so let's start today's presentation. And today I'm happy to present you Lalli Myllyaho from the University of Helsinki, and he will be talking about validation methods for AI systems. So please go ahead, Lalli.
Okay, good morning. So I'm Lalli, working as a PhD student at the University of Helsinki in the empirical software engineering group and in the IVES project specifically, which is concerned about these testing and validating and other machine learning related functionality ensuring stuff for, well, mainly industrial level machine learning, but also, why not, overall stuff. So the presentation is based on my recently published paper, Systematic Literature Review on Validation Methods for AI Systems, the DOI of which you can see on the screen if you're interested in actually reading it. I'm going to be, well, first I'm going to explain a couple of terms to make sure that we all know what we're talking about, and especially that I hopefully remember from there on what I'm going to talk about. Then I'm going to present the problem itself, then go briefly over how the research methodology works. I presume not everyone is familiar with how systematic literature reviews work, but I'm going to keep that brief so I won't bore you to death. And then we'll go to the results. First, I'm going to be shortly presenting what kinds of systems were found, and then to go the actual validation methods. So first off, validation. Well, we all here probably know that validation has also a specific meaning in machine learning, but that's not what we're talking about here. But we are talking about the validation as understood in software testing, which means it's testing that the system works as intended. Basically, with the idea, well, the example I've used before is that if there is an autonomous car which drives from point A to point B, you can say that it works. but if it runs everyone over along the way, it doesn't really work as intended. So validation is to test that these kind of unwanted side effects do not remain in the system, and also that it's doing what it was supposed to do. Then the paper is actually focused on what we called in the paper practical AI systems, which means that they are complete systems, so not just models, but also some other software to make it usable to someone, and it performs. Then the practical side is that it performs a purposeful function in a realistic context, meaning that it is something that someone could actually use for something. So, for example, if it's just a model that maybe tries to detect whether or not there's a dog in the picture, as is, it's not of interest to us here, but it should be used for something actually. Then, but why? And that's a fair question. I think there are three main reasons why the validation of not just the models, but the entire system, and in the context of machine learning, is something that should be of concern. And first, the machine learning has implications on the system. We know that the machine learning is it's whimsical, when compared to traditional software. Traditional software usually has some well-defined problems and well-behaving sort of problem fields that you can have test some pretty straightforward test oracles for. You put the stuff in the for example, in an online store, you put the stuff in the shopping cart, and then you go and pay it, and it pretty much does what it does, hopefully, and you know when it does what it does. But with the machine learning and with the promise of some sort of intelligence, it may not be that straightforward. So knowing how to test the systems that have this sort of unpredictability to it should probably be taken into account some way. Like, for example, when if you have some system that's recommending you what to watch next, which video to suggest to you, that's something that you don't really know what the correct answer actually is, because even the wrong answer, in a sense, can be good enough. Another thing is that the application domains of many of intelligence systems may be, well, the scale and the complexity can be something completely different. Again, with the autonomous cars, it should be efficient, it should be reliable, it should be safe, it should be whatever. And in the sense, and in the case of the autonomous car, it should be able to drive off to the badlands of a Terrence Malick film and come into a crossroads with 7 other cars, 3 pedestrians, 2 of which are drunk, with a pothole in the middle, none of which it has ever seen before, and somehow it should handle the situation and preferably not kill everyone along the way. And at least to me, that's it's not really self-evident how to validate that. And third, what we've learned from traditional software, again, is that people are actually pretty good at making mistakes on all levels when making systems. So even with the traditional software, when you're testing it, there are many levels of testing. There's the component testing and integration testing, and then we go to the system testing and on the validation side that it's actually doing what it should be doing. And with the traditional software, again, there isn't really, or at least usually isn't something that's at least trying to be intelligent. So even if the model itself has been validated and it's fairly good, then you could implement it wrong. You could, maybe the data that it receives turns out to not be exactly like the data it received when it was trained and stuff like that. Then the systematic literature review, you can see the outline. That's a picture from the paper. That's how it basically works. I'm not going over all the laborious details, but basically it's a rigorous methodology. Now I twisted my tongue. Well, you can read the word method. Yes, let's go with that. To find relevant papers for the problem you're seeking. Basically, you form a search string that you think will find stuff that you want to find, use it on several databases, find a terrifying amount of papers, and then through some criteria you define, you throw stuff out and hopefully end up with a reasonable amount of papers that are actually relevant to you. And in our case, what we wanted to find were some believable practical systems that are appropriately validated, or some believable validation methods for practical systems. Sorry, papers that describe either of these. And by believable, I mean that it's somehow reasonable for the problem it's supposed to be doing, and then again that the validation is appropriate considering the problem it should be solving. For example, if there would be something that the authors claim to be an elderly care robot, and then it's validated by having it run around a box in an office, then it's not exactly appropriately validated for what it's supposed to be doing, which would be roaming around an elderly care center and somehow communicate with the elderly or something like that. And yeah, so basically what we found, we had an initial set of more than 1,100 papers, and then I had to go through all of them in a couple of phases, and then we ended up with 90 final papers that we actually used in the paper and the analysis. Then some results. Like I said, first let's go through roughly what kind of systems we found, and here you can see the domains and the tasks that the systems were performing. And in my opinion, I was actually a bit pleased that we found many domains and tasks, and which suggests that it hopefully suggests that the search was successful, and B, it suggests that the machine learning has practical use in wide variety of domains beyond the initial promise that it will have. Because at first I wasn't entirely sure that it is the case yet. I hoped it did, and it turned out it does. But then again, as you can see, it's very much more popular in some domains than others. Well, there's some consideration in the paper that why that could be the case. Maybe I won't go through that here. And with the task side as well, it's the wide variety of tasks suggest the some usefulness in any contexts, but again, the recognition and classification for, perhaps unsurprisingly for this audience, is very, very popular. But then, to the actual methods, finally, might someone say. Here you can see the basic outline of the sort of shallow taxonomy that the validation methods we found had. And it's basically in 4 groups: simulations, trials, model-centered approaches, and expert opinions. And with the first 2 having sort of subgroups within them. The blocks, sorry, I think I might sneeze. No, I didn't. The blocks represent the relative commonness among the papers, which methods were used more and which one were used less. Like, for example, you can see that the expert opinions weren't very common, whereas trials in real environments are. very much the opposite. But I think, well, I thought we would go through the actual validation methods and have some short idea of what it is, and maybe an example from them. So first, the fully virtual simulation, which is quite self-evident from the name, I hope, because I tried to make them descriptive. But the idea is that the system and the environment are modeled in a virtual simulation. For example, with a again with a car, it's an easy example for everything. Gives me easy escapes. But the car, for example, an autonomous car would be it would have an avatar in a virtual city or whatever, in which the sensory data would be everything would be computer generated, and then the software of the car would then try to calculate and decide what to do next and what not to do. For example, if there is a pedestrian crossing the road, the avatar should stop and hopefully in a reasonable amount of time. But these were highly popular with cyber physical systems like cars and robots, and they a clear benefit they had, I think, is first of all safety. If you are validating the car, you'd probably want it to crash into people in the simulator rather than in the real world. And also there are results. God damn, I was supposed to have the paper mentioned here. Oh, forgot. But anyway, there are some results where some people have calculated that to have a reasonable certainty that the autonomous car would be safer than a human driver, then it would have to drive some millions of kilometers or something like that, which is somewhat unreasonable perhaps in a lot of cases. So having these simulators allows to probably test them in a much faster pace. In addition to the safety side. The downside is that if the simulator isn't accurate, then you're probably in a lot of trouble, because even small deviations may be actually significant, especially in sort of close cases, when the car should be braking suddenly. If the simulator says that, okay, it manages these situations, but then the simulator isn't accurate, then in the real world it means that it will kill the pedestrian in perhaps 100% of the time in those situations. Next, hardware in the loop simulations, which is that the simulations are mostly virtual, but there are some non-virtual components in the setup. And an example of this, there was a paper in which a truck convoying system was tested, with the basic idea that there would be some lead truck and then the others would follow autonomously. and the trucks in this case were modeled again in a simulator, but one of the follower trucks, it had this sort of physical setup of driving wheel and brakes and the gas and all these components that you usually have in trucks that would serve as the sort of measurements for the outputs, that when the simulator and the software would tell the truck to do something, then the actual driving wheel would turn and the physical brake would be hit and whatever. And then these physical actions would then give again feedback to the simulator, and the avatar would hopefully do what the hardware told it to do. And compared to the fully virtual simulator, I think that it had the upside that it would probably have it would be a bit less prone to mistakes in the simulator, because if the wheel would turn and the truck in the simulator wouldn't, then you would obviously know that the simulator is faulty and has to be tweaked. And also another benefit would be that this kind of simulation would tell us something about the communication of the software and the hardware, because again, as I mentioned earlier, the integration of different components in the system is something that's usually pretty prone to problems. Of course, you cannot use this if your system doesn't have any hardware, but which can probably which is probably quite self-evident, but mentioned it anyway. Then we have system-in-the-loop simulations, and here the entire system is deployed, but the validation environment is something that is clearly artificial. And here there were some cases in which the environment would be physical. So there was a it was a rescue robot, I think, if I recall correctly, that for saving people in mining stops. And for that, well, for a couple of reasons, they built a sort of a test stop, small test stop in which they would validate the robot, because if you're sending your expensive robot in a test run to the actual mining stop, you won't have any communication with it, probably, because mines usually don't have that good of an internet or whatever, and there will be thick walls and twists and turns and whatnot. And also the winding stops can be pretty dangerous. So if you lose your robot in there, then you probably lose the robot. So what they did was that they tried to identify different kinds of surfaces and different kinds of problematic situations and scenarios in the actual mining stopes, and then they built something that would closely resemble it in terms of the surface, so that how the robot would see in the mine. So how the surfaces reflect and whatever, and yet they wouldn't be losing the robot if it turned out that it doesn't work. And why I decided that this was a simulation was that because the setup was quite artificial to me. Instead of exactly they were replicating the features of the real environment instead of the real environment, and that to me seemed like a simulation. And again, the simulation can be virtual. For example, there was which was pretty cool, I think. There was a for an autonomous car, there was a the car had some test ground, which was basically an empty garage where it would drive around. But the car and its actions were replicated by an avatar in a virtual simulation. And when in the simulation, they received some inputs, data, and garage or whatever, and then the real car would have
I'm sorry, Lalli. I think that we now lost your voice. At least I guess it's not just my network, but
I also
yeah.
lost Lalli's voice.
Should we shut the cameras, or maybe if you at least you try to shut the camera, so. Okay, we don't hear you yet either. Oh. Okay, can you hear us, Lalli? Okay, I'm sorry, we can't hear you. So maybe Markus and me we should also turn off the camera. So. It's okay. I think I can see that you are trying to speak, but at least I don't hear anything. Please let me know if someone else has different situation. Okay, now at least I heard something.
So you hear me now?
Now we hear you.
Or,
Yes, now we can hear you.
oh, great. Where was I cut off? Or does it matter?
I think just before I said so, you can just continue where you ended.
Okay, I was actually going to the next slide. Then we have a trial in a real environment, which again, hopefully is pretty self-evident. It's using the system as it should be used. Again, one cool example was there was this. It was a game that was meant to aid doctors to determine whether or not children suffered from ADHD or not. And they would have children, it was sort of a platformer game, and then it would, based on how the kid would play the game, it would have a guess, and it would be used as additional info on whether with other method, actual other kinds of, well, sort of the normal process of diagnosing ADHD. And they would have kids which had gone through the normal diagnosis procedure, which would either be diagnosed as having an ADHD or not, and then they would play, and it would be based on this. It was said that it works or didn't work. I recall it worked fairly well. Anyway, heavens the time. Then there were trials in a sort of mock environment, which is that the validation environment wouldn't be exactly the sort of final environment, but somehow something that replicates it or is a simplified or miniature version of it. For example, there was some system that tried to, well, based on a person's heartbeat and whatever, it would try to play the music that would help them be more efficient in while they're studying. And this was tested. Well, it was used for what it's supposed to be used in, but it was tested in a laboratory. So considering that laboratory setting is something that people usually don't study in, but it's a simplified version of the real environment. There's no noise, there's no other people, there's no books on the shelves, and you don't have to do the dishes and whatever. So it was sort of a mock version of the real world instead of the actual version. Sorry, I'm trying to be quick now so that we can get this done. Then there were model-centered validation methods, which are basically the idea is that if the model works, then the system will. They were very common with sort of simple systems, which might have been basically a model and a user interface for it, which in the sense doesn't sound unreasonable, especially if you have enough of good quality data. Then you can test the system fairly fast with a lot of inputs. And it was also often used as a sort of initial validation before trials or simulations. But basically, often model validation as understood in machine learning in general. And finally, there was this sort of expert opinion, which was fairly rare, and it seemed less rigorous and more like like a walkthrough that was presented by the developers to some expert of the application domain. For example, a firefighter would be presented with some system that would try to, for example, suggest how many units should be sent to a fire site and whatever. These showed, according to the papers, these showed the greatest value of these was to have sort of more knowledge on what is important and what is not in the system when the expertise was not present in the development itself. We recognized something that I gave an umbrella term, continuous validation, which were basically some measures that keep on making sure that the system works as intended. For example, when the systems some of them keep learning after deployments, then how to know that it keeps on being what it was supposed to be. Basically, this consists of fault tolerance measures and watchdogs and other sort of other measures. But these were rarely reported. B, they usually weren't described in much detail, and C, even less often any of their success was reported. So it was difficult to make very strong conclusions out of them, and that's why this is actually what I've been doing research on since, and maybe we'll hear about it some next time. Shortcomings of the paper, well, first of all, it's based on research literature, which means that it would be bold to make very strong statements about the state of the industry, and also the results are very dependent on the success of the methodology, which requires a lot of subjective interpretations at times, and that's of course always raises some questions on the results, and that's what I see as intelligent or believable or useful or appropriate and whatnot. It's very much up in the air. But in summary, the machine learning has turned out to have practical use in a variety of domains, even if it wasn't often applied in all domains. It was sometimes used in many domains. And then the simulations, trials, model-centered approaches, and experts were the basic groups of validation methods that we found in the papers. If you have questions, we have maybe a couple of minutes left, and this took more time than I thought. But if you come up with something later, you can email me, and here's again the toy for the paper if you're interested in. Thank you for listening.
Okay, great. Thank you, Lalli, for the interesting presentation. And we are then looking forward to hearing for the next results then on the next presentation. But we would have time for one quick question if there is any in the audience. So please, you can just open your mic or raise a hand. So while the audience is still thinking, so I could start by asking that you were presenting the topics for the tasks of the presented system in your of the papers that you had been looking at, and then there was only 4 addressing the safety of the system. So do you have any comment for that? Because that was quite surprising for me.
You mean here?
Yeah. So there are only 4 papers addressing the safety topic.
Oh, right. Sorry. I didn't. It isn't exactly the safety of the system, but it's a system that's used for some safety measures. So the application domain is safety. So it could be, I cannot recall what it is, but it could be, but what the papers were, but it could be, for example, a surveillance system or something like that.
Yeah. Okay, but still it is quite surprising that that topic is addressed only in 4 papers. But okay, great, thank you. So are there any other questions that have arose in the audience? Okay, so it seems that not, but okay, so again, thank you very much, Lalli, for the presentation, and thank you for everyone for listening, and please stay tuned. So we will be sending more information about then the continuation of the machine learning coffee seminar, and of course putting the topics for the new presentations into the web pages. So please follow that too. But then for everyone, so have a good week and see you again next time. Bye bye.
Thank you. Bye.
Thank you.